Let's look at some of the properties that breadth first search has. After one call to breadth first search from some starting vertex, we visit all of the vertices and edges of the connected component that that vertex belongs to. And secondly, if we only take the discovery edges that BFS marks and we don't include any of the cross edges, so the discovery edges alone induce a spanning tree of that connected component. The discovery edges were exactly what we had used in order to discover all of the vertices of that connected component. And by eliminating the cross edges, we're just getting rid of any of those extra edges that we had. So we have that the discovery edges induce a spanning tree of that connected component because we have every vertex included. Remember what a spanning tree is. This is spanning that entire connected component in the sense that we include every vertex of it. And this is also a tree because we have no cycles. Any edge which would have formed a cycle was one of those cross edges. This was leading back to a vertex we had already encountered. So we get a spanning tree by taking only the discovery edges. In fact, we get a spanning tree for each connected component that we have. So the result of our original breadth first search call for our entire graph is a spanning tree for each connected component, which means we get a spanning forest. And then thirdly, this is a property which is unique to breadth first search. The other two I mentioned also hold for depth first search traversal. But if we're using a breadth first search, because of how we added vertices, first we process everything which is one edge away from our starting vertex, then everything which is one edge away from the previous layer, and then the next layer we form based on anything which is one edge away from the previous layer. Because of that, then if we have some vertex, let's say V, here's a vertex V, which belongs to layer I, so any layer, then that means that in our spanning tree, we had a path from our starting vertex, so in this case this was our starting vertex, to this vertex V, which used only I edges. So for example here, this is 1, 2, 3 apart. This is our layer 3, based on how I drew it. And every vertex in layer 2 has a path to our starting vertex using only 2 edges. Everything in layer 1 has a path to our starting vertex using only 1 edge. So the layer that a vertex belongs to corresponds to the length of a path from our starting vertex to a vertex of that layer. And in fact, every path from our starting vertex to that vertex has at least that many edges. So this is saying something more. This is saying not only does this path have I edges if this vertex belongs to layer I, but every path has at least I edges. So that's really your shortest path because any other path we could find has at least that many edges. And the reason for that is if we could reach this vertex using less edges, then we would have included that vertex in an earlier layer because we only ever form the vertices that belong to this layer based on those new vertices that we couldn't reach before, that we could only reach through some edge of the previous layer. So this is an important property of breadth first search, which is unique to breadth first search. Now let's see, how efficient is breadth first search? Let's go back to our algorithm. So we mark every vertex and edge as unexplored. So to mark every vertex, this takes linear time big O of n to go through each of the n vertices, and to mark each of the m edges as unexplored as big O of m time. Now we go through every vertex, check to see if it's been unexplored. So just these 2 lines is total big O of n. And then we call breadth first search on each unexplored vertex. Now as a result of this breadth first search call, we end up visiting other vertices as well. But we'll only call breadth first search once for each connected component of our graph. So we're going to add up the total cost of however many times we have to call this, however many connected components we have, and see what the cost of this would be. So this is for each connected component we have to do this. Let's identify first what constant time operations we have. So we create a sequence, we add elements to a sequence in constant time, we can set or get labels in constant time. check if our list is empty in constant time, create new sequence in constant time. Again, getting or setting a label, getting the opposite end of a vertex, these are all constant time operations. Adding to the end of a list, these are all constant time operations. The only question is, how many times do we perform these constant time operations? And this is for every vertex of every layer, we go through every incident edge. So this is for some layer here, this is our layer I, we have maybe a few vertices in it, and those vertices have some other incident edges. And we'll traverse each of those incident edges. That's what will give us our next layer, layer I plus 1. Whatever vertices we were able to reach. But how many times do we really have to do this? Because at a first glance here, it looks like we have 3 nested loops that maybe this would be n cubed time, but this is not a very good analysis. Instead, let's observe that of all of the times that we call BFS, not just this first time, but of any particular time, that a given vertex belongs to only one layer at a time. So this is a unique relationship. So each of the n vertices in our graph belongs to only one layer. And then we go through each of those vertices of our layer. So by processing every vertex of every layer, we end up processing just all of the vertices in our graph. We're just doing this on a layer by layer basis. So we perform this operation ultimately for every vertex in our entire graph, if we look at all the times we call BFS. And for every vertex of our graph, we go through all incident edges of that vertex. Now, some vertices have more or less incident edges. This is based on the degree of that vertex. So again, we come back to the total times we execute this across all BFS calls is based on the degree of each vertex. And if we add together for every vertex in our entire graph what the degree of each vertex is, then from the handshaking lemma, we know that this is 2 times however many edges we have. So our total running time for all of the calls to BFS is big O of M. So for breadth first search, entire running time is big O of N plus M. Now we can apply breadth first search in order to compute a spanning forest of our graph. In fact, we get one spanning tree per connected component. These are spanning trees which are induced by just the discovery edges, which also allows us to find all connected components, because we end up getting a spanning tree for each one of them. If we have only one connected component, then our graph is connected. If we have more than one connected component, then our graph is not connected. We can also use this in order to find a simple cycle. So again, if we have a cross edge, the existence of a cross edge means that we've got a cycle in our graph. Or we can use this to find a path between 2 vertices, or report that no path exists. So similarly, we can, to report that no path exists, we could label every vertex based on which spanning tree it belongs to. So just to give a numerical value, an integer for this belongs to the first, second, third spanning tree, which corresponds to the first, second, third connected component, and so forth. If there's a path between vertices, then they have to belong to the same connected component. Or we could, knowing that there is some path, we could find a path between vertices by starting our breadth first search at that vertex we want to find a path from, and then layer by layer work through our breadth first search until we stop at some vertex, and then just follow the discovery edges that we used in order to get to that vertex. So we can use this breadth first search applied to all of the problems that we had wanted to solve before. And in fact, we also find between these 2 vertices a shortest path, and in this case, because we have an unweighted graph, a shortest path just means that we're using the least number of edges. So we'll see how this compares to depth first search in the next video.